Let's review series. You need to be able to deal with any one of these forms, either of them. So a sub 1 plus a sub 2 dot 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 all the way to a sub n dot dot dot, or summation notation. We're going to be doing a lot with both of them, but especially that summation notation. S sub n is the nth partial sum, i.e. S sub n equals a sub 1 plus a sub 2 all the way to a sub n. A series can be made into a sequence of partial sums, i.e. s sub 1, s sub 2, s sub 3, all the way to s sub n. So we can use a series to find these. S sub 1 would just be the first term. S sub 2 would be the sum of the first two terms. S sub 3, the sum of the first three terms, etc. All right, our focus, just like when we are dealing with the sequences, is does this series converge or diverge? If the series converges, what is the sum? All right, so if we look at this and we say, if this converges, and this is just the notation, we're talking about the nth partial sum from n equals 1 to infinity. It converges to s, i.e. the limit as n goes to infinity of s sub n is s. Then the series converges. And the sum is s. If this diverges, then the limit as n goes to infinity can equal infinity, negative infinity, or it just doesn't exist. And that doesn't exist. As before, it could oscillate. All right, then the series is going to diverge, or the series diverges. So go ahead and write the following down. Basically, if the limit exists, i.e. it goes to a number, then the series converges. If the limit does not exist, the series diverges. Let's look at some series you already know, geometric series. Let's just take a quick review of it. We have two different ways we can write it using summation notation. K equals 0 to infinity of a times r to the k, or k equals 1 to infinity of a times r to the k minus 1. So we have a plus ar squared all the way ar to the n minus 1. If we're going to infinity, that keeps on going. And if we're looking at s sub n, then we're going to be stopping at n. And so again, either form, this is going to now stop at r to the n minus 1. And what is that sum? That will be a times 1 minus r to the n over 1 minus r. And this is a good idea that you should know how to prove this thing. I'm not going to do it right now. So we have s equals the limit as n goes to infinity of s sub n, or in other words, the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. Now, what's being affected by n? Only this part, and we reviewed that yesterday in the last video. So we have a times 1 minus, well, in this case it's going to depend what the value of r is. And I'll write it down in a second. If r is less than 1, then this thing is going to go to 0 over 1 minus r. So we get either a times 1 over 1 minus r or a over 1 minus r if the absolute value of r is strictly less than 1. Now, if you have anything else, absolute value of r is greater than or equal to 1, then the geometric series diverges. So we're going to be using this. We want to be able to recognize it. One that maybe it's not so clear immediately is if r equals 1, but you can think about it. If you're adding, in essence, a plus a plus a plus a an infinite number of times, you're going to infinity. Assuming a is positive. It could go negative infinity. All right, let's take a quick one on this. So I like this picture. It took me a while to try to make it, but this is a proof, a picture proof of this here. All right, so for right this second, let's write it out. This is going to be 1/2 when k equals 1 plus 1/4 plus 1/8, etc. Now, you have to get used to looking at this. Since this is starting at k equals 1 and this is 2 to the k, it's not the exact form that we just went over. But it is still geometric. We still have a common ratio of 1/2, but the first term is 1/2. So we have s equals, I'm going to put that, since it's a fraction in front, times 1 over 1 minus 1/2, and that will just give us 1. And if we look at this picture, and we have, it's a 1 by 1, we cut it in half, there's a 1/2, we cut the rest in half, there's a 1/4, and we continue that. Eventually, towards infinity, every last bit gets filled in, and that is 1. All right, let's look at a couple examples. I'll go through them quickly. We have here, this is in our form, the absolute value of 3/4 is less than 1, so this thing converges. What does it converge to? We have our first term will be 5, and then 5 times 3/4, so it is the correct form. We have 5 over 1 minus 3/4, 5 over 1/4, so we get 20. On the next one, we can look at it and say when we plug it in, that's going to be 1, so we have, it also is in the correct form. So we can just plug it in. We have negative 6/7. Let's check, is less than 1, so this converges. So we get s equals 2 over 1 minus negative 6/7. 2 over, that's plus, so that'd be 13/7. So this sum would be 14 over 13. And the last one, it's not in the correct form. So what we want to do is we want to put in the form, and it really doesn't matter which one, but the standard one that you would have done last year would have been k equals 1. So we have k equals 1 to infinity a times r to the k minus 1. And we have that k equals 1 here. So we're going to, let's pull the 4 out, and we just need to manipulate this a little bit. So 5 to the k plus 1 is going to be the same as 5 squared times 5 to the k minus 1, since k minus 1 plus 2 is k plus 1, over 3 to the k minus 1. So we can pull that 5 squared out, and we'll have 100 sum k equals 1 to infinity of 5/3 to the k minus 1. And since 5/3 is greater than 1, this thing is going to diverge. Now, since this is a positive, it's going to diverge to positive infinity. Let's look at it, something that's a little different. What if it's not geometric? Well, what we can do is find the partial sums. So let's look at the first 4. So we have s sub 1 will just be that first term, 1/2. The next one will be 1/2 plus 1/6. And when we simplify that, we'll get 2/3. 1/2 plus 1/6 plus 1/12. That gives us 3/4. Let's do one more. 1/2 plus 1/6 plus 1/12 plus 1/20. And that will give us 4/5. I did the stuff, but you could check me to make sure. So let's write a formula for s sub n. On the top, we have just n. On the bottom, we have n plus 1. Let's look at the limit as n goes to infinity of n over n plus 1, and that's going to equal 1. So that is the sum of this series. That's one way to do it. Another way to do it is to recognize that we've seen this type of thing before. That is something that we could use partial fractions. So we can put here, recognize partial fractions. So we can set it to a over I plus b over I plus 1. Go ahead and clear it all. We'll get 1 equals a times I plus 1 plus b times I. Now let's just, again, we can do it easy. We'll just substitute I equals 0. That's going to take out the b. So we'll get 1 equals a. And then if we say I equals negative 1, then that's going to take out the a part, and we'll get 1 equals b times negative 1, or b equals negative 1. So this fraction will be 1 over I minus 1 over I plus 1. Sorry, I couldn't quite see that. There it is. But I think you know that. Let's now rewrite this sum as 1 over I minus 1 over I plus 1. And let's write the terms out. So if we plug in 1, we'll get 1 minus a half. That's our first one. Plus, if we plug in 2, we get 1 over 2 minus 1 over 3. And let's continue doing this. Plus 1 over 3 minus 1 over 4. And we'll go dot, dot, dot. And that last one, well, since we're going to n in this case, the last one will be 1 over n minus 1 over n plus 1. And what's nice about this one, looking at here, is look at how we have negative 1/2 and positive 1/2. Negative 1/3, positive 1/3. And it continues, negative 1/4, positive 1/4. We'll have negative 1 over n, positive 1 over n. So all of these middle terms are going to go away, and we're going to be left with 1 minus 1 over n plus 1. Now if we find the limit as n goes to infinity of this, remember to put your parentheses on it. This term's going to go to 0, so we get 1. In other words, the sum converges to 1. This, when you can write something like that, this is called a telescoping series. This is when the middle terms go away and you're left with just a few terms. Now in this particular example, we're just left with 2, the first one and the last. But it's possible you have maybe 2 terms here and 2 at the end, or 3 terms here and 3 at the end. But the telescoping series is when you can write that, and those middle ones will go out. All right, next one. Let's look at an example. We're going to take this repeating decimal. We're going to convert it basically into a fraction. We have the first part, which is 0.6. That's not a part of the repetition, the repeating part. So we have 0.05. We have a placeholder 0 for this 6, plus 0.005, plus 0.005, plus dot, dot, dot. It goes on forever. The repeating part would be here. Now, just as an aside, if let's say this had 2 decimals that repeating, like 54, then we'd have 0.054. We would need a placeholder for all 3 of those over here, and that will also affect when we are writing the sum part, what these values are. Our first term in this case is 0.05, and r equals 1/10. But if I had 2 that were repeating, then r would be 1/100th. let's write it in summation notation. The only purpose of writing in summation notation is to just get some practice. You need to be very comfortable with writing pretty much anything in summation notation. If you have a problem like this, in general, you don't need to do that. So we have 1/10 to the k minus 1. We'll have 0.6 plus, this is an infinite geometric series, so we can say 0.05 over 1 minus 1/10. And at this point, we can just simplify that. That is 1/20th divided by 9/10. And that will be, flip and multiply, we'll get 1/18. So this will be 3/5 plus 1/18. And simplify that, and we'll get 59 over 90. All right. This next one, this is an important test. You need to know it well. The nth term test for divergence. If the limit as k goes to infinity of a sub k does not equal 0, then the sum diverges. Think about this for a second. We're adding an infinite number of terms, and the last term doesn't go to 0. So we keep on adding more and more and more and more, so it should make sense that this thing is diverging. I.e., if the last term does not approach 0, the series must diverge. All right. If the sum from k equals 1 to infinity of a sub k converges, then the limit must equal 0. So, i.e., if the series converges, then the last term approaches 0. So now, what if the limit of the sequence approaches 0? That last term is going to 0. What's going to happen for that? Well, let's take a look at an example. K equals 1 to infinity of 1 over k. We can have the limit as k goes to infinity of 1 over k. That's going to give us 0. Let's take a look at here. So we're going to say, all right, this part here is 1, and we have a half. What I want to do is look at the groupings of powers of 2. So here, and basically starting from a power of 2, the next term, all the way to the next power of 2. So we'll go 1/9 all the way to 1/16. And what we're going to do is make a substitution for this, and we're going to take out the 1/3, and we're going to put in 1 over the power of 2. When we do this, since 1/3 is greater than 1/4, this original sum is going to be more than. And let me group these together. Let's do it for the next part as well. We're going to take 1/5 all the way to 1/8, and we're going to make them all 1/8. We do it again for the 1/9. That'll be 1/16 plus all the way down to 1/16. And then we continue on this. Now we can count these parts easily, but how many 1/16ths do we have? 1, 2, 3, 4, 5, 6, 7, 8, which should make sense because we're taking 16 minus 8. What happens when we add these up? We have 1 plus a half plus 1/4 plus 1/4 is 1/2. 1/8 plus 1/8 plus 1/8 plus 1/8 is 1/2. The next one, we have 8 of them, so it's 1/2. So now, how many of these do we have? We can continue doing this from 2 to the k to, well, let's say from 2 to the k minus 1 to 2 to the k. So when we subtract that, that's going to end up giving us our power of 2. And can you continue this indefinitely? Yes. So what does that say? We're adding 1 plus a half an infinite number of times. So we have 1/2. In other words, this series diverges. So we have the sum from k equals 1 to infinity of 1 over k equals infinity, and that diverges. So then, write the following. Remember the comparison test for improper integrals. It's the same. What did we compare to for the improper integrals? Was 1 over x from 1 to infinity. Now we're looking at the exact same thing. So, what does limit as k goes to infinity of a sub k equals 0 tell us? Nothing. Nada. Zilch. So, we need another test. It could diverge or converge. So, again, right, it's important to keep the nth term tests for divergence clear. It only works for divergence. It's the first test to use. Highlight that note, make it stand out, because we're going to be using it often. All right, let's look at a couple problems here. So determine whether the following series converge or diverge. If it converges, find the sum. So what we're going to do is we're going to use that nth term test for divergence and say the limit as k goes to infinity of 2k minus 5 over 7k plus 1. What does that go to? 2/7. That's not equal to 0, so therefore this thing diverges. Let's do it again, but something that looks a little bit more complicated. So we have the limit as k goes to infinity of k factorial plus 3 over 2k factorial minus 1. So what we could do here is divide each term by k factorial to get 1 plus 3 over k factorial. 2 minus 1 over k factorial. Those terms are going to 0, so this goes to 1/2. Again, that's not equal to 0, so this thing diverges. When we look at the last one here, what we want to do is recognize that this is a difference of geometric series. This is a difference of geometric series. So let's just split it up. We have k equals 0 to infinity of 1 over 2 to the k. You can write it like that, or I'm going to rewrite it on the next one and we'll just write it as 1/3 to the k. Either way, it doesn't make any difference. The first one would be 1 over 1 minus 1/2. So that's going to be 2 minus 1 over 1 minus 1/3. And that's going to be 3/2. So this is going to give us 1/2. So this thing converges, and it converges to 1/2. And that's it.